So far in our videos, we've been talking about the ionic compounds, the binary ionic compounds of just the elements in the S and the P subshells. So clearly we have, and even when we drew that periodic table with the +1, +2, +3, and then the -1, -2, -3s, okay, even there, clearly we left out, and I didn't draw the periodic table there, but there's that D subshell that we have not talked about at all yet. Okay, so it's quite obvious we've left that out so far. Okay, and really the reason why that we've left them out is because, like for example, that first column is always +1. Okay, the second column is always +2. The problem is those metals that are, again, let me actually draw the periodic table here. Basically, again, we've got our +1s, +2s, our -1, -2s, and -3s. And then our +3 here, the +3 here really just applies to those first two elements here, boron and aluminum. Okay? Basically, any element that is between this line right here, and then there's a stair step. So here's boron, here's aluminum. Starting between them, there's a stair step that goes down like that. So it finishes between numbers 84 and 85. So if you have a periodic table, it might be a good idea to put that stair step in there. Because really what that does is it separates the metals from the nonmetals. Okay, and these metals in here are called the transition metals. Okay, and one of the reasons they are called the transition metals is because their charges can change. Okay, so the reason that we've left the transition metals out so far is because the majority of them do not just have just one. Now here's a fancy word for you. It's called the oxidation number. The oxidation number just means the charge. Okay, so most of these elements in here, in that transition metal area, can lose a different number of electrons. They don't always lose the same amount. Like this column here always loses 1. This column always loses 2. This column always gains 1, etc. The transition metals, they're metals, so they always lose electrons, but they can lose a different amount of electrons. Okay, and so this is where it gets a little bit trickier. So let's start with iron as an example. Okay, iron is number 26 on the periodic table. It obviously has 26 protons, 26 electrons, but iron sometimes has a charge of +2, which means sometimes it loses 2 electrons, and sometimes it has a charge of +3, meaning it loses 3 electrons. Okay, so when we put those two together, when we create the formula for that, if we're talking about iron with a +2 charge and oxygen, if we're going to put it together with oxygen, iron has a +2 charge, iron has a +2, oxygen has the -2, so it would create just FeO. Okay, but when iron has a +3 charge and oxygen has the -2 charge, again, remember we take those numbers and we switch them, so you get Fe2O3. Okay, those are two very different compounds. Okay, this one here is the chemical formula of rust. Okay, so and iron, the other iron compound is not. The problem is, so that's fairly easy. When we know the charges and we have to write the formula, we do just like how we did before. We just switch those charges and we write the chemical formula. Okay. The problem is if we use the same rules we learned before about naming them, this would be called iron oxide and this would be called iron oxide. But they are two different chemical formulas. Yeah, but they both have iron and oxygen. Well, it's kind of like the difference between H2O and H2O2. H2O is obviously water. H2O2 is hydrogen peroxide. And if you start drinking hydrogen peroxide instead of water, you're going to find out very quickly that one little oxygen difference makes a huge, huge difference. So we can't call both of these iron oxide. So to name an ionic compound that has a transition metal in it, it's very, very similar to what we did before. You write the name of the metal, so you list the name of the metal, so iron, and iron. In both cases, obviously, it's iron. And then it says, in Roman numerals, you write the oxidation number, which again just means the charge, of the metal in parentheses. And then the name of the nonmetal at the end changed to IDE. So this is iron, and notice I'm leaving some space there, oxide, and iron oxide. Okay, so in parentheses, so I'm going to put some parentheses here, you're going to put the Roman numeral, and again, this is not a Roman numeral class, okay, 1, 2, 3, where it gets tricky with Roman numerals is 4, is IV, V is 5, and then 6 is VI, 7, you're not going to have anything bigger than that. And if you get that wrong, I'm not too worried about it, okay? If you're like, crap, I can't remember what 4 is, and you write the number 4 in there instead, I'm not going to, it's not a huge deal. Technically, that is how you do it, though, is you use the Roman numeral, and the Roman numeral represents the charge on the iron. Okay, so in this case, iron has a +2 charge. So therefore, this is iron 2 oxide. Okay, and that's how you would say it, is you would call it iron 2 oxide. Okay, in the bottom one, the iron has a +3 charge. So you write iron 3 oxide. A very common mistake that students make is students will look at this and go, oh, there's only one iron here. That's iron 1 oxide. And here there's 2 irons, so it's iron 2 oxide. Okay, it's never, well, it could be just by coincidence, but it's not the number of iron atoms there are. It's the charge on the iron atoms. That is the key. Okay, so I just talked about both of those. So what are the names of CuO and Cu2O? Okay, it's very simple and wrong to just call the first one copper 1 oxide. That's what I just talked about. And the second one, copper 2 oxide, based on the number of copper atoms. You don't base it on the number of atoms in the chemical formula. The reason it's wrong is because, again, the number in Roman numerals is equal to the charge or the oxidation number on that copper ion, not the actual number of copper atoms. Okay, so the question comes up, well, how are we supposed to know what the oxidation number is? Okay, you have to use the nonmetal. You have to use this part right here. You use this to figure out the charge on that. Because remember, the charges must cancel each other out. They must be equal and opposite. Okay, so in this case, oxygen has a -2 charge. If oxygen has a -2 charge, the copper must have a +2 charge in order to cancel those charges. Okay, so in this case, CuO is therefore called copper 2 oxide. Okay, that's CuO. Okay, Cu2O, again, oxygen is -2, and copper is +2, or copper all total has to be +2. But since there's 2 coppers, here's how you have to think about this. If there's 2 coppers and the overall charge has to be +2, each copper therefore must have a charge of +1. Okay, and so therefore this is copper 1 oxide. Okay, because again, the charge, think if you have this, think if you have Cu plus and O2 minus. What's the chemical formula of it? Well, Cu2O. See how it's copper 1? Okay, so that's why it is copper 1 oxide. Okay, now, any of those transition metals, remember from that line over all the way over to the stair step, they all can change their charges with 3 exceptions. Now the nice thing is it goes in a nice diagonal direction. So it goes aluminum, zinc, and silver. So it goes down diagonally like this. Aluminum always has a +3 charge. Zinc always has a +2 charge, and silver has a +1 charge. Now, the reason that's important, it means that with these 3 elements, plus those first 2 columns, the +1 and the +2 columns, the hydrogen column and the beryllium column, you don't use Roman numerals. And here's where it starts to get, you have to remember, do I use Roman numerals here? Do I not use Roman numerals here? You only use Roman numerals on elements whose charges, whose oxidation numbers can change. If they don't change, then you don't use Roman numerals on it. Okay, and some of these examples will be like that. as well. Okay, so the first ones, let's start over here. Actually, this side's a little bit easier than the other side, and hopefully by doing this side first, it'll help us. So this says cadmium 3 fluoride. So that means that cadmium, remember, the Roman numeral tells you the charge. So that's cadmium. That means it has to have a +3 charge. Because again, you find cadmium on the periodic table, it's in the transition metal area. Well, I don't know the charge on it. That's right, and that's why that Roman numeral has to be there. And then F- means that it is CdF3. Okay, magnesium phosphide. Where's the Roman numeral? You don't need one. Okay, the reason you don't need one is because magnesium's in the second column. Magnesium is always +2, and then phosphorus is -3. So switch those, Mg3P2. Okay, scandium 3 oxide means scandium has a +3 charge. Oxygen always has that -2 charge, so it's Sc2O3. Okay, here's one that's a little bit tricky. Cobalt, it says is IV, that's a +4. And then sulfur, or sulfide is from sulfur, that's -2. Normally you would switch those, and you still can, but if you can reduce them, you have to reduce them. And by that I mean, if you write CO2S4, I'm going to mark that wrong, because it's not 2 cobalts and 4 sulfurs. Because if you think about it, if this is +4, don't we just need 2 of these to make that -4? And see how if you go, oh, what's a number I can divide both of those by? I can divide them both by 2. Then you end up getting just COS2 is the correct response. So if you switch them, which again, you can always do, just make sure that if you can reduce those values, you have to reduce them. Okay, platinum 2 nitride is platinum with a +2 charge. Nitrogen with a -3 charge, so it's Pt3N2. Gallium 1 selenide would be Ga+, and then Se. Selenium has a -2 charge, so that would be Ga2Se. Thallium is Tl with a +2 charge. Bromine has a -1 charge, so TlBr2. See how this Roman numeral really helps? Copper 1 is Cus, or Cu with a plus charge, and then S2-, so it'd be Cu2S. Tin 4 oxide is going to look very similar to this one up here. You're going to have tin with a +4 and oxygen with a -2. So again, to cancel those out, you just need the 2 oxygens. So you're going to have SNO2. Okay, and again, you can switch them, but then you do have to reduce them. And then our final one here on aluminum chloride. Aluminum, again, does not need a Roman numeral because it's always +3. Chlorine is -1, so we get AlCl3. Okay, over here on the right-hand side. Again, I always start these out by, okay, I'm going to write titanium, and then I look and I go, oh, yep, it needs a Roman numeral, so I'm going to leave a little space in there, and then I'm going to write chloride. Okay, and now I just have to figure out what is that Roman numeral. Okay, and it's the same thing with all of them. Does this need a Roman numeral? Absolutely, yes, it does. That is tin something sulfide. Okay, this is going to be gold something bromide. See how that's the same thing as before? We just have to put those Roman numerals. Okay, zirconium something phosphide. Okay, but no, ooh, if you catch it, you got to catch it. Ag2O is just silver oxide. No Roman numeral needed because, again, remember, silver is one of those ones. Silver's always a +1. Okay, and that same thing's going to happen right here on G where you've got zinc. Okay, you don't have to put zinc Roman numeral. It's just zinc iodide because zinc, like silver, always has a +2 charge associated with it. Okay, so this one, Pb, is lead. And it is going to have a charge. Okay, manganese nitride And again, obviously I'm doing this quickly, but you need to be looking at the periodic table and deciding, do I need a Roman numeral or not? Okay, and that's oxide, and then vanadium, also oxide. Okay, so now we just need to figure out the Roman numerals. Okay, chlorine's -1. There's 4 of them. That's -4. So titanium has to be +4. So it's IV. Okay, sulfur's -2. So tin has to be +2. So it's tin 2 sulfide. Bromine's -1, and there's 3 of them. So that's -3. So the gold has to be +3. Phosphorus is -3, so the zirconium has to be +3, so they'll cancel each other out. Okay, letter F, oxygen's -2, and there's 2 of them, so that's -4 all total. See how I did that? Each oxygen has a -2 charge, but since there's 2 of them, that's -4. So that means the lead has to be +4. Okay, here's a tricky one right here. The last 3 are a little bit trickier. Okay, so nitrogen has a -3 charge, and there's 2 of them. So that makes it -6 all total. So that means that the manganese all total has to be +6. But there's 3 manganeses, so 6 divided by 3 is +2. So that means that the manganese is 2. Okay, so manganese 2 nitride. Okay, oxygen, again, notice how I'm starting with the nonmetal every single time. Oxygen's -2, so the mercury has to be +2, but since there's 2 of them, each one of them must be +1. So that is mercury 1 oxide. And then our final one, oxygen's -2. There's 5 of them though, so that's -10. That means that the vanadium must be +10, and +10 divided by 2 is 5.